This information is brought to you by Charles Sturt University.
So yes, we'll do Boolean algebra. Let's get ready. Oh, so far, hopefully. Okay, so morning everybody. Hope your long weekend was restful, good, whatever you want to. I think it was to be. So I want to just finish off the section of Boolean algebra. So George Boole did his logic stuff over 100 years ago. That's where the stuff came from. But as the idea of computers was developing, they realised that they could use a lot of this sort of stuff to the logical circuits. And so that's what we're doing today, and I think you've seen some of this already perhaps in ITC 161, so you can tell me all the answers. So nowadays you just use transistors on a computer to do all this sort of stuff, which builds it all, and so you can use transistors to model all these sort of different ands, ors, knots, etc. And so what I want to do is want to get from any, so basically want to have a logic circuit pretty much has a bunch of binary inputs, and then you want to produce some sort of output from it as a result of it all. So we call it an n-ary Boolean function, is a very fancy way of saying it. Essentially you've got a bunch of 0, 1 inputs, give an output. And what that really just amounts to saying is, we'll look at a truth table, that's what it normally boils down to. Now the set of all such n-ary Boolean functions is a Boolean algebra, so it has all the normal properties of Boolean algebras, and therefore has the nice simplification rules you can have, etc. And we can, therefore the set of logical circuits on n inputs would again be a Boolean algebra. And you can swap between the two quite happily. So the main thing is just the equivalence. So let's see if you can remember stuff. Wait to get this thing up. Yeah. So pretty much our main operations that we consider, and or not. So we want to have the, or in terms of Boolean algebras, multiplication plus and the overline. What's the equivalent in terms of logic circuits for each of these? What's the equivalent for what's an AND gate essentially?
It's a D.
Yep. So you can have at least 2 inputs. You can have multiple if you wanted to. What about an OR one look like?
The curve, just get it's a smooth chevron.
It's a bit more pointy at the end, isn't it? Something like that.
It's smooth though. So it's a smooth chevron. It's not like perfectly pointy.
That's what I think it to be.
Yeah.
And the knot?
Okay.
Triangle and circle. That's the only one I can remember.
So
What was the XOR key?
the circle is the key attribute to the inverter. So that's called an inverter.
The NOR one is just a circle on the NOR is a circle on the tip of the...
Yeah, so if you put circles on the end of an AND gate, or an OR gate, you put a circles on the end of it, it just negates the whole thing. That sort of idea. So and, or, and not. Okay, they're the simplest ones. And as strictly saying, there are NAND and NOR gates as well. Pop a little circle in the end. And XOR.
It's like the same as the OR, except with an extra
That's right.
thingy.
So just these three is enough.
Doesn't a not gate also take 2 inputs? Does the not gate also give 2
No,
inputs?
it just switches the input.
It just switches from, basically the NOT gate goes from 0 to 1 or 1 to 0, and therefore all you need is 1.
So you have to use 1 input.
Yep, 1 input.
So we're not going to have to use the XOR gates at all.
No, so I mean, as a matter of fact, you can do the whole thing with a NAND gate. Just use one type of gate, does everything. If you really wanted to do that way. So there's no harm in putting more in, but that's sufficient to all our other purposes. So we'll be here too. As you realise, if you're trying to do an XOR, for example, then to do an XOR by itself is a combination of a few of those. And so sometimes that's a simpler way of writing it down at times. So they're key logical circuits, or the key conversion between them all. So for nodes you can do anything. So you can add things together. So addition really involves 2 operations. One is you actually have to add the digits together, which is the add one over here. And then the second thing you need to carry, if there's an overflow, you have to carry it to the next one over. So what are the logical circuits for each of these? So what's the logical circuit for carry, for example?
And
So just AND. So that's an easy one. This is one single gate. What about add? What's the actual addition?
that'd be an OR.
So OR would be...
It's an XOR.
Right. So it's an exclusive OR. It's one or the other, but not both.
Yeah. It's exclusively OR.
So the add operator, so X add Y, and it's just adding, we're just adding one bit at a time, is the same as saying X or Y, which stands for exclusive OR. Which you could write you can do a nice little simple gate for it. How can we represent it in terms of the things we know already though? So let's just do the truth table. So X and Y. So when you add the two together, you get 0, 1, 1, 0. That's the adding operator. So if you're adding 1 and 1 to itself, you get 2, which in binary would be 1, 0. So the 1 overflows and the 0 stays around. So how do we represent this in terms of ands and alls and nots? Any ideas? So if you're in a bit of a loss, the key way, which I'll mention more explicitly next few slides, is to use the sum of products form, which is also called the disjunctive normal form. So you've got a truth table. So you just go to the truth table. Whenever you see a 1, you just look at those rows by itself. And you write down the corresponding expression for each of those rows. So this first row corresponds to X being off and Y being on. That's equivalent to X being off and Y being on. That's the product form for that particular row. The next row would be X being on and Y being off. That's the product corresponding to that particular row. And you just add them all up. So that's the idea of a sum of products sort of form. So you just look at all the rows that have a 1 in them, and then just work out a particular form and add them all up. Did you do that sort of idea? I'll do it in a bigger example where you can see it more clearly, but That's one way of doing it. So you just go each row, work out the corresponding expression, which would be a product of either x's or y's or the complements of them. So in terms of what we know, that's not x and y, or x and not y. That's sort of what that's putting in terms of the logical operators. Now you could write that differently if you wanted to, but let's just try to do that. So let's do a logical circuit based on just that expression as it stands. So basically we need to have the inputs x and y. If you look at it, we need to know what both not x and not y are in a second. So really the last thing we want to do is we want to all things together. So that's our sort of last operation. So I'll track that on the end. Then we want to all two things, and they are just two different ands we're adding. So these sort of sum of products form, how it really works is you do lots of ands, that corresponds to each of the individual products, and you do all of all in one go. That's the default design. It isn't always the best, but it always works at least. So this first gate here, this first AND gate's got to be not x and y. So I want to feed in y directly. And I want to feed in the not of x. How do you do not again? A triangle. So it's not x and y being fed into. So again, let's just think about it. That's not x, that's y. This is not x and y coming out of that gate. That's that. All looks good. For the second gate, we want to have x going in, and then the not of y. So again, we've got to chuck another inverter in there to make it a not y. So coming out of this one, we've got y bar, this one's x. Coming out is x and not y, and the end result is not x or, so not x, y, or y not x, not y, which is a very long way of saying x or. And so the other way of writing the whole thing down, for short, is that gate. It's the same thing. Which you can see why people use that abbreviation. That's not the only way of doing it. You could do it as a OR gate minus a, so OR and the not AND. But the sum of products is a good way of doing it. So you can see even simple operations can sometimes require a few expressions to put it all down together. So what we want to do is we want to give any sort of Boolean function, normally involving possibly many inputs, we'd like to devise a way of trying to get a simplified logical circuit, one which has the least number of gates we can think of as possible in it. There's a few different ways of doing that. So first, this idea is called the disjunctive normal form, which perhaps more helpfully is called the sum of products form. They are the same synonyms. So as I said, how you work this thing is you work out the truth table for your Boolean expression, the Boolean function, and look at the rows. They just have a 1 in them, essentially. Everything else you ignore. For each of those rows, you translate it into the corresponding expression, which will be a product, and then just do the sum of all those things. Let's do an example to make it easier to see. So this is a Boolean function defined by its truth table. So what I want to do is do a few things. First of all, let's just write a sum of products form for it. That's one way, and then we could just do a logical circuit based on that straight away. However, before doing that, it's probably better to try to simplify it if possible. So I want to look at two different simplification techniques. So first of all, let's look at all the ones. So the first one here is that first row. That corresponds to all the values being off. So the expression for that would be x being off, y being off, and z being off. So it's basically not of all the three variables. The next one we want to concern about is the next one here. What would the product form for that row be? Yep. Yep. That's it. The next one.
X, no, Y and Z.
Yep. And two more to go. Next one along.
Is it X, not Y, and Z?
Yep. And the last one, do them like as well.
X, Y, not Z.
Yep, X, Y, Z bar. So that's the disjunctive normal form. And again, it's just a straight translation. So from that, we could do a logical circuit based on that straight away. So for each of those products, we'd require 2 AND gates for it to work, and a few inverters chucked in there probably. So because there's lots of knots everywhere, you need 3 inverter gates to get the X, not Y, not Z. For every product you need 2 ANDs, and then being generous, we could do 1 OR gate which has lots of inputs if we want to not have to write things down over too much of the time. And again, you could do the same thing with an AND gate. You could do AND with 3 inputs just to save some room or allow that sort of thing to happen. But still, we'll have to do an AND gate for each product and an OR gate to pack them all together. So there's a few things to do there. Can we make it simpler? So can we simplify this expression? So a few ways of doing that. One way is to use the laws of Boolean algebra to try to simplify it down. So because we're comfortable with factorising with products, we could do that. We could factorise some things out, and that sometimes helps. So that's one way. Can anyone see anything that jumps out of you? The answer is probably perhaps not. So the way I prefer to do it when the expressions aren't getting more complicated and nothing does jump out at me, I would prefer to using a Carnot map. That's my preference for that. But I mean, just to show you some techniques if you can't do that, is to say like I'm trying to factorise things out. So you're looking at if you're looking at anything in sort of common. So if you look at these two terms, just for example, both of them have an X and a Z bar in common between the two of them. So I could factorise the X, Z bar out and live with Y bar plus Y. What's Y bar plus Y going to be? 1. So that's just equal to X, Z bar. So I can factorise, if I just see two matching terms, most terms are in common, factorise common terms out, and you can see the simplification happening. And you can do the same thing quite a few times in that sort of process. But it's hard to keep track of it all, so I prefer Carnot maps. So I mentioned some Carnot maps in the last lecture, just for the simple case. So I want to do the same thing for 3 variables this time. So for Carnot maps for 3 variables, basically we're going to have, the truth table has, as we can see, 8 different entries in it. So the Carnot map has to have 8 different entries in it too. So I've got variables X, Y and Z. So on the rows here, I'm just going to label as X and not X for the 2 variables. On the columns here, I basically want to represent all the different options we have for y's and z's. So either both being on, one being off, one being on, and two being off. That's the same of the idea. But I want to do it in a way that adjacent labellings have only one difference between them. This is called a grey code. So to start with, just put y and z, so both being on. Then I want to change one thing at a time. That's the key. That's the key thing to remember. So we change one of them. Which one should we change first? Your pick.
Z.
Okay. So therefore we change the z to y z bar. We have to change one more thing to get the next one. Now we've already changed z, so I'll change y next. Otherwise, where we started from. So the next one would be y bar z bar. Again, I have to change one more thing. We just changed y. So let's change the z this time. So it'll be y bar z. And that's a grey code. So if you think in terms of the numbers, that's 1, 1, 1, 0, 0, 0, 0, 1. That's the corresponding binary code for it. And you can see that's not in a normal sorting order. So it's called a grey code in that sense. And so the key thing, you have to make sure they're all adjacent. That's the key thing. And if you had 4 variables, you do the same thing. You do a grey code going down as well as across as well. So now we've got that. We now just put ones into all the different entries. So we can look at our truth table here. And whenever we've got a 1 in our truth table, we just put a 1 in our Carnot map. So you can see the first one here is when they're all off. So that would be here, when they're all off. Next one is X is off and Y and Z are on. That's a 1 there. This is when X is on and Y and Z are both off. This one is X and Z are X is on, Y is off and Z is on. So that one there, I think.
No. When X and Y are on, but Z is off. Wait, no, I'm looking at the next one. Don't worry.
Yeah, and then this one here. So if X is on, Y is on, Z is off. That's the one there. And that's it. So I've got all the ones. And we put zeros everywhere else just to remind us all that are supposed to be zeros. So that's so basically we just translated the truth table into this diagram. You're just keeping track of what we've done here. So how Carnot maps work, like I mentioned the other day, is you're trying to find blocks of size powers of 2. So size 1, 2, 4, 8, 16 if you've got that big, for example. So looking for blocks of that size. They have to be rectangles, and that sort of idea. And you're looking for as big as you possibly can. Can you see any blocks of size 8? Well, no, because there's a few ones in the way. There's a few zeros in the way. And they're going to be covered just the ones by themselves. So can you see any blocks of size 4? No. So what about size 2? We can see a few of those. What sort of blocks of size 2 can we see here? So these blocks have to cover just the ones. So let's just do one of them, for example. That one, so I can have a block of size 2 covering up those 2 entries. Now, whenever a block, each block corresponds to some sort of Boolean expression. So if we look at this block, just the one coloured in red there, basically this corresponds to the whole column corresponds to Y bar, Z bar. X need to be on or off, so it covers both options. So these blocks always simplify down to something else. So the other one's a bit more interesting to look at. Well, the sort of blocks, we can do this one here, for example. So in this particular case, in both those entries, X is on. So X is on for both of those. What else is common between the two of them?
Not Z.
Not Z. And Z can either be on or off, so both options are covered, so therefore we can drop it out. Which corresponds to that precise thing we just did over here. So you could do the same thing by direct simplification by factorising, but this one takes it all care of it for you. You can see where you need to pull these things out, etc. Another block of size 2 would be this one here. So what's in common for those two entries? So they both have a, sorry that? Yeah, they both have an X and they both have a not Y. The Z is either on or off, so it's both of those covered. So that's the simplified expression for it. So the reason why we used a grey code is because they always have adjacent things next to it, and therefore this simplification works nicely. Now we haven't covered quite everything yet. So the last thing we need to do is this one over here, which is sort of by itself. You can't cover it with a block of size 2 at all, so we really are just stuck with what we've got. And so its corresponding expression would be not X, Y, and Z. So in this sort of, in the three variables, a block of size 8 would correspond to 1. Block of size 4 would be 1 variable. Block of size 2, like we've got here, are 2 variables. Block of size 1 is 3 variables mentioned. So that expression is a little bit simpler than what we had to begin with, which is sort of the whole purpose for it all. And we could do a logical circuit based on that. So we've got X, Y, and Z. So when you've got a complicated expression, I would always split them up straight away. And put inverters for each of them. Because we're going to need them, probably. If I don't, I'll write them out afterwards. I can do that easily, you can't always admittedly. So this is X and not X, Y, not Y, Z and not Z. And then we try to chuck them together. So the first term we want is an AND of Z bar and Y bar and Z bar. It's our first one. Another AND gate of X and Z bar. Another AND gate of X and Y bar. And the last one is not X, Y and Z. And I could just, I'm using an abbreviation there, so when I put an AND gate with 3 inputs into it, that's just being lazy, and I could write it more fully as 2 AND gates, one feeding into the other. That's a sort of shorthand. And what I want to do with all those expressions?
Put them through an OR gate.
Yep. And again, being lazy. If I want to do it fully, so if I didn't want to use the an OR gate with 4 inputs, if I just wanted to use the proper OR gate, which just have 2 inputs, how would you have to do it? So technically speaking, an OR gate really is only can do 2 at a time. I just combine 2 things at a time. Yeah. And so if you had to do 3 of them, you do OR of 2 first to get a result, and you get all the next one along. So do 4, you do the first 2, then you add the next one on, and the last one on. So the number of times, the number of OR gates required is the number of difference between them. So there's 3. So there's 3 gaps between my fingers essentially. So technically you could do that with 3 different OR gates. I think it's for sake of space on a piece of paper. That's okay. So that's the, and that might look bad, but it's better than if we'd done it without simplifying it. So just something else, just the Carnot maps. Just want to look at a different one here. So this is a different expression with a different Carnot map. So I just want to show you something else you can do with these sort of things. So you can see the expression at the top, just a sum of products form. So again, we want to do blocks as big as we can. So like before, we had a block of size 2 here, which corresponds to what? So what sort of things are in common for everything in the circle there?
Not X and not Z.
Yep. So not X and not Z are the things in common. So that's what that one corresponds to. What else can we want to do? So you might. So there's 2 other ones you need to cover. So it might be tempting to put another block of size 2 at that point in time, if you wanted to. But a trick here with them all, which is why I mentioned this example, is because of how we've used grey code, it actually wraps around. So I can choose a block which includes those 2 ones in the end. So this is the trick you need to learn about these things. So because the YZ at the beginning and the YZ bar at the end are really adjacent to each other. So you want to think of it, it's actually a ring, and then it wraps around, joins it to their ends. So there's a block size 2 we can put up on the top. So what is common between those 2?
It's the Y. It's the Y.
So basically, both because it's in the same, because they're both in the X row, X is on for both of them. Otherwise, the Y is common to both of them, but the Z is either on or off, can be either or. So it's both options are covered. So it simplifies down to just X, Y. So the trick with these Carnot maps is because when you start using the grey code, you can wrap it around, which makes things nice and powerful. So you can get bigger, more simplified expressions that way, or more simplifications. And that particular expression, that's the simplest you can probably go really. You might be tempted to go, look, I can put another block of size 2 just there and write another expression down. But because all those entries are already being covered with what we've done, we're just adding something which isn't required. So that wouldn't actually help. So I could, if I wanted to, say plus Y, Z bar. I could chuck that on the end if I wanted to. That's still correct. It's exactly the same expression. But it isn't actually helping because the most simplified expression is just that. So you could keep covering up the map with more and more blocks if you wanted to, but if all the ones are already covered, you should just stop because you're not going to get any better. You're not going to get any better, and you're trying to have as minimal coverage as possible. Now, for a block size, if you had for 3 variables, the same sort of thing approaches. If you had 4 variables, the same sort of thing applies, which I'll do an example of in a second. Anything higher than that Carnot maps that works so very well, and so that's when you start using a computer algorithm to do it for you. But it's the same idea. It uses the same sort of approach as it's just generalised to an algorithm. But these ones work well for visually. I don't know if Optimize has bothered doing this sort of stuff to your code or not. If they can go, look, you got some horrendous Boolean statement in your if, can I work it out and make it simpler or not? I don't know. The other thing that computer code normally does is short circuit logic. So it doesn't bother working out all the expressions unless it needs to. And so, and therefore there's danger if you want. You can't simplify things greatly that way necessarily, because you don't have to evaluate them all before you want to start simplifying. So that's the main. So I'll do the 4 variables as an example, but that's the main theory that we're finishing off the subject. So I'll do the 4 variables case so you can see what things look like. But you can see the Boolean algebra section really just sort of rounds off, just closed off what we started with at the beginning. And Boolean algebra just sort of collects that idea of set theory we began with and the set of logic that we use, truth and false, etc. Puts them all together, links it with the logic circuit, and just shows that they're all highly connected to each other. And any result in any one of those different problem areas are essentially equivalent to each other. So the things that I want you to be able to know is you need to know, in inverted commas, the properties of Boolean algebra. And what does that mean? It means you need to look them up from a piece of paper in your exam, essentially. You do need to know, it is worthwhile knowing some of them off the top of your head, like De Morgan's law. And some of these are actually useful when you're doing coding for. Okay. So you go, like I'm doing an if statement, I know, hold on a sec, I've got an and, for example, as my clause in an if statement. Oh no, it's actually making more sense to me to swap it around to make that the else clause. And you have to do then you have to do the negation of what's up the top here. De Morgan's law is a useful way of doing that. So knowing some of them, and the other one, there's lots of them fairly straightforward. I'll like to suggest. De Morgan's law perhaps is not so straightforward when you first see it. So you need to know them. You need to know how to prove some things. So we'll do some practice that in tutorials, and I did that more in the last lecture. You need to know this idea of the duality principle. What's that again?
Swap the ands with alls and the zeros with ones.
Yep. So if you get any expression, if you swap basically the dual of any expression in Boolean algebra, swapping ands and alls and zeros and ones, that gives you the dual. Why that's important is if a Boolean expression is true, then its dual is automatically true as well. And you can say therefore you see that with most of the Boolean algebra properties, they tend to form in pairs, and the pairs are the duals of each other. Given any truth table or any Boolean function, we need to be able to work out the disjunctive normal form and be able to simplify it down, either using the rules or using the Kano maps. They're equivalent to each other, and knowing these logic circuits as well. So you need to know what the pictures are. And again, you can do that by having them on your piece of paper you bring to the exam. That's also acceptable. So, I mean, if you ever do these things again, you should always look at them up, I'm sure. But in practice, most of the things you probably want to do is knowing their simplification techniques is probably more critical. So they're the key things I want you to take away. And again, your exam has 5 questions, 1 question per topic. And question is a bit of a loose term, really. It's a collection of questions. So the question on Boolean algebra would be these sorts of things. So I'll look at one of the sample exams next week to give you a feel for what your exam is going to be. So I'll mention more of that next week. So how about we let's do a 4 variables case of a Kano map. I don't have to draw the whole truth table out. So you have to do grey code. So at the top, so if you've got 4 variables, then it's 2 to the power of 4 or 16 different options for the truth table. So there's my grid of 16 numbers, 0 is 1 for the truth table. So again, I want to do grey code. So for the top, same as what I did before. YZ, I'll do exactly the same as we had before. YZ bar, Y bar, Z bar, and Y bar, Z. So again, just changing one at a time, and do the same thing going down. So WX, and again, just changing one variable at a time. And again, they're grey codes, isn't that adjacency idea? So let's just put some ones in here and we'll go for it. So let's put some ones here and here. So imagine that's our truth table. And you can do anything you want to at all. What's the so a few things from that would be, what would be the disjunctive normal form? That's the first thing. What does that mean again? So sum of products form. What's the sum of products form for that function? So for each one in the truth table, or the function effectively, so each output of the function, which is 1, you just write the corresponding expression for it. So we'll start it. We'll probably get too bored to write the whole thing down, but anyway. So that 1, for example.
Expressions.
Yeah, I know. So you can say we don't really want to have to use this disjunctive normal form. So that 1 there, for example.
WXY.
So we W, X, Y, Z. That'll be the first one. Let's just do the first 3 and then we'll say dot, dot, dot. What would the next one be?
WX not YZ.
Yep. So again, just matching up the expressions for it. Next one along.
W not X YZ.
Yep. And again, there'll be 1 per 1 in the table. So as you said, 9 expressions there. So what I want to do, I know we could utilise that, make a logic circuit based on those 9 expressions. Can we make it better than that? Can we make it more simpler? So we want to simplify it. So I just simplify it. Again, we're trying to get blocks here, which are as big as possible. The size of the blocks have to be some power of 2. That's the basic restriction. So again, we're trying to pick. Biggest block you get is 16, but that's not possible because there's a few zeros or blanks are written in there, so it's not going to work out. Any ones of size 8 we can get.
What do you mean by size 8?
So that would be a block like that. That's a block of size 8. Or it could be like that. So those 4 on the ends. Or it could be that's a block of size 8. So they're examples of size 8 that we would look for. And you can see none of the ones that Drew just worked. So I think the answer is no. There's no blocks of size 8. What about size 4? Can we get any ones of blocks of size 4?
Yeah. You got 2 and you got 1 there and then 1 there.
So you've got the ones on the outside. Yeah, that's one of them.
And you got the 1 below.
We've got another block of size 4 here. So let's write down the expressions that they correspond to. So again, for these 4 entries, so whenever you can, so every power of 2, you drop a variable. So if you've got a block of just size 1, in this particular case, it'll have all 4 variables present. If you have a block of size 2, you drop 1 variable, you only have 3 present. Block of size 4 drops another 1, you get 2 present, etc. So you should be able to simplify it down to just 2 variables. So you've got to work out which 2 variables are common between all 4 of those ones in red there. So W is common between those 2 rows, so you get the W part, and in terms of the 2 columns, Z is common between the 2 columns, so you get W and Z. Does that make sense to people? So the X and X be either on or off, either option, so that just cancels out. It can be either option. So with the green, again, we should be able to simplify down to just 2 variables.
So it's not Y.
So not W, not Z.
was thinking W, but I said Y.
Okay, so that's our block exercise 4 that we can do. Now we're trying to. Now, what would you do next? So you're gonna get. There's one last one to get there.
Write that down.
I wouldn't. I would combine with block size 2, something like that. Choose as big a block as you possibly can to include it. Makes it a little bit easier. That's not the only choice by any means. You could have just chosen block size 1, but I'll choose a block size 2. What would that correspond to? So you should have 3 variables present.
Yeah, not X, not Y, not Z.
So the not X is common, the Y bar and the Z bar is common. So since it's all in the same column, the whole column, the variable for the expression for the whole column has to be present. Because it's 2 entries, it's simplifying something on the rows here. Now I could have written down just the one here by itself, which would be W, X bar, Y bar, Z bar, and I could have put plus that instead. That's also exact. That's also equal. But why I chose a bigger block, because it makes this expression just a little bit simpler. Not by much really. That's why I did that. Chose a bigger block. So the bigger the block makes it simpler whenever you can. So as you can see, it's the same sort of idea for 3 variables. So 3 and 4 variables really work the same sort of way for Carnot map. And that expression at the bottom is much nicer than the disjunctive normal form we had in the first place. So, and you could do the same idea if you with other different circuits. So let's just let's rub a few out. Say we had a few D's. What does the D stand for? The D stands for I don't care if it's on or off, essentially. So why would you ever do that? Is because you're designing a circuit and you know that I'm never going to get that variety of inputs are never going to rise in a situation that I'm concerned about. So you can say that's a precondition effectively. So I really don't care what they're about. That is because it will never occur from my consideration. So I can make that a 0 or a 1, whatever I feel like, essentially. So again, we do the same trick. We want to make them go and choose blocks as big as we possibly can each one at a time. And so again, we pick the block for size 2. Now with those don't cares, so what would you do next? So that's the same first step. What would your next block be?
Can you do diagonal?
No.
Okay.
Very ridiculous and too easy.
I thought you could have.
No, the reason why I can't do diagonals is because diagonals would correspond to some sort of XOR. So you could do XORs maybe if you wanted to go that way. But if you just want to do simple expressions, which we're trying to go for, we can't do diagonals.
I have no ideas then.
So again, we want to try to use blocks of size, biggest blocks we possibly can. Now, we want to choose these 2 ones. We need to cover those up somehow or other. It's best if we cover it by as big as possible because that makes things simpler. So we can utilise these 2 don't cares to make it a slightly more simpler expression. So we'll use them because we can. We still have to cover this one. So something like we did before. The last don't care, well, we don't need it for anything, so we just won't bother utilising it. So you get the same expression as I had before. So you can use these Carnot maps for other sorts of logic design. Now, again, from your purposes, that sort of detail would happen by an optimizer for your compiler, if it does it at all. Operations are much quicker than they were when they started doing these things. It all adds up though. So if you have a inefficient code which is running lots and lots of times.
Yeah, that's what I'm about.
So you do need to there are key code that you do need to make sure it's optimal.
It's going to be at least 5 seconds in boot time on the compiler. Anything below 5 seconds is unacceptable. Just run through a whole bunch of nested loops over and over. That's the real.
You've got to see it work.
Yeah, we've got to make sure it all works.
Yeah, if you're just waiting there, twiddling your thumb for it to start up, yeah.
It's the best job.
So that's some idea of simplifying stuff. As I said, nowadays there's an algorithm which just does that for you, which I presume if benefits be coded up. But it's the same sort of idea, and understanding that concept is helpful for you. And you would have anything more complicated than that. I just hope you're not dealing with it directly in your code. You probably want to break it down. But you might want to deal with compound Boolean expressions at times, but definitely in computer code you do. So having some idea of how you can simplify it down and manipulate it, like taking complements and breaking it down, is a useful concept. So I will leave there today. So we'll do some practice on this in the tutorial this afternoon, and then next week we'll look at your exam. Or the sample exam, therefore getting ready for your real exam. The sample and your exam aren't the same. Catch you getting hyped up for a second.
You are currently the only participant in the conference.